Good morning to everyone. My name is Jesper Eriksson, and I'm the VP of Product Management at NoviFlow. And today we're going to talk about segment routing. But first, I want to introduce NoviFlow and put segment routing into some perspective. NoviFlow was founded in 2012 by 4 telecom executives. We're based in Montreal, Canada. Our focus is on software-defined networking and scaling cybersecurity. Our core products is our SDN network operating system software that runs on white box switches. And our SDN-NOS runs on Mellanox network processors, as well as Intel Barefoot Tofino Silicon. Our business is to license and support our software to our customers. Our customers are mostly major carriers, large enterprises, and governments. Since the start of the company in 2012, our focus has been on making networks more programmable. Through OpenFlow and P4 runtime, we expose a programmable match action pipeline to application programmers. And then what is a match action pipeline? If you look at the picture on the right, you see a set of tables. The tables make up a match action pipeline. In each table, the packet is matched on some packet header field, and then some action is taken to the packet. As an example, in the picture on the right, there is a mitigation table where you may match on the IP source address in the packet, and then the action may be to drop the packet. The match action pipeline is an extension of the application and does what the application wants it to do. You can look at the tables as functions executed on the packet on behalf of the application. The picture on the right shows tables for mitigation, load balancing, and forwarding. It also has a table called new functionality. And this is really up to the imagination of the application programmer, what they want to do. And then on top of the match action pipeline abstraction in our NOS, we have built controllers and applications that leverages this programmability. The end result is a fully programmable stack. At the top of the stack, you have the NoviFlow applications such as CyberMapper. These applications run on top of a P4 runtime controller. The controller interacts with the NoviFlow NOS in the switch and the P4 program running in the Barefoot Tofino programmable switch silicon. All this software runs on white boxes and commercial off-the-shelf servers. With this fully programmable stack, NoviFlow is able to innovate through software at every level of the stack, from the application to the switch silicon. On this slide, we see 3 distinct ways that you may program the behavior of a network. These 3 ways are not mutually exclusive and are often used in conjunction. The first way is to program a network at the orchestration level. At this level, you program the configuration and state data of the network devices. The network devices configuration and state data is abstracted through some standard YANG model, data model, and then this data may be pushed or read from the device through a netconf or GNMI protocol from a controller. This way of programming the network is used when you have distributed switch and routing protocol stacks. The match action pipeline is hidden behind the protocol stacks. A key benefits of this level of programmability is to automate the provisioning of legacy network devices and speed up provisioning of these devices and eliminate manual errors. The second way is to program the match action pipeline of the network devices. Here, a set of match action flow tables are programmatically defined through either OpenFlow or P4. At runtime, a controller pushes flow entries into these flow tables using the OpenFlow or P4 runtime protocols. The match action pipeline and the flow entries define how packets are processed by the network device. The application interacts directly with the match action pipeline in this way of programming. And the key benefits from this level of programmability is that the network device may be easily evolved in regards to functionality over time, and you actually also separate the path computation engine from the protocol stacks. The third way is to program the packets themselves. The technology for this is segment routing, either over IPv6 or over MPLS. As the packets enters the network, it is classified, and based on this classification, an ordered list of instructions are inserted into the packet itself that defines how the packet will be processed by the network. The key benefits of this level of programmability are traffic engineering, service chaining, and making network services addressable. Segment routing is a variant of source routing. The headend or ingress router insert this ordered list of segments into the packet that defines how the packet will be processed in the network. The segments represent instructions to the network that are executed by the segment routing aware routers in the network. These instructions are not only forwarding to next hop type of instructions, but also more complex instructions such as encapsulation, decapsulation of the packets. Segment routing works either on IPv6 or MPLS data planes. In an MPLS network, the segments are encoded as MPLS labels. In an IPv6 network, an Ipv6 extension header called the segment routing header is added, and then this segment router header contains an ordered list of segments encoding the instructions that the network will operate on the packet. Please note that segment routing is an additional capability to an existing MPLS or IPv6 forwarding node. And not all MPLS IPv6 routers in the network need to be segment routing capable. Here's an SRv6 example and shows how a network may process a packet. So imagine host X wants to send a packet to host Y on the other side of the network. Host X sends the yellow packet to router A, which is the SRv6 source router, which classifies the packet and steers it onto an SR policy by inserting an SR header with an ordered list of segments, in this case, YHFC. And it changes the destination address to C, which is the next segment. Router B, which is SR unaware, just forwards the packet to the next hop, which is router C. And then router C, which is SR aware, updates the destination address and the SR header and forwards the packet to the next hop. Router F, the NoviFlow's CyberMapper, is SR aware and executes the service function associated with the SID. This could be sending the packet to one or more load balance pools of security services. CyberMapper then updates the destination address and the SR header and forwards the packet to the next hop. Router G, again, another SR unaware router, just simply sends the packet on to router H. And then the router H, which is SR aware, is the last SID in the list and decapsulates the packet and forwards the original packet to host Y. A few observations on what happened. It is the ingress router and not the host that steers the packets onto an SR policy. This is why SRv6 is called a variant of source router. The packet was steered through the network through a specific pre-engineered path, and traffic engineering is a classic capability of SRv6. The packet was also steered through one or more network services as it traversed the network. SRv6 allows you to programmatically service chain different network services that you want the packet to go through before it handed off the other end. These network services are addressable in the network through the SIDs that the router advertise. This is very different to how things are done today, where most network services are hardwired into specific physical locations in the network. Here is a brief introduction to the NoviFlow's CyberMapper. CyberMapper is a NoviFlow solution that provides a number of network services that operators need in their network. It consists of the CyberMapper application and controller that leverages the capabilities of the NoviWare NOS running on Barefoot Tofino white box switches. The Threat Intelligence Gateway service is a way for operators to block certain traffic from getting onto their network. CyberMapper will execute any deny list directly in the Tofino silicon and do so much more efficiently than on an x86. An example of a deny list is the deny list published by the Internet Watch Foundation. The packet broker services include things like filtering, mirroring, and port pairing. The load balancing services are built on top of a sticky and stateless load balancer implemented directly in the Tofino silicon. It supports proportional load balancing and the ability to dynamically grow or shrink the pool of load balanced physical or virtual security services. Networking services include in-band network telemetry for security services, latency, performance monitoring, SRv6 routing that allows the security services to be globally addressable and service chained in the SRv6 network, and SRv6 security services proxy that allows the operator to associate one or more security services load balanced by the CyberMapper to an SRv6 segment ID or SID that is then advertised to the network. This slide shows how CyberMapper with SRv6 can be used in a mobile network. Traffic from the left or the mobile subscriber is sent through one or more network services in the mobile backhaul before it is forwarded to the mobile core. Traffic from the right or the internet is sent through one or more network services on the GI LAN before it is forwarded to the mobile core. The specific set of network services on the backhaul and GI LAN vary by operator, and CyberMapper is already in production performing load balancing of security services on the backhaul and GI LAN. This is the end of my presentation. Thank you for watching, and I hope you found this interesting and useful. If you have any questions, please feel free to visit NoviFlow's website at www.noviflow.com or give us a call. Thank you.